Okay, welcome back. Let's continue thinking through how we're going to identify unknown organic molecules in experiment 2. So after you've obtained the solubility data discussed in module 1, you should have an idea of where on the list of possible functional groups your molecule might lie. Carboxylic acid versus phenol versus amine. And if your solubility data didn't indicate one of those key acidic or basic functional groups, you know that it's likely you probably have a ketone, an aldehyde, or a nitrile, or a generic alcohol. To help us solidify the functional group class, we're going to be looking at IR spectroscopy data, and then we're going to try to narrow down which molecule within that functional group class we have using some additional data. So let's talk about IR spectroscopy, which you've seen in lecture. Okay, you'll recall from general chemistry that light has an associated energy. Okay, and we use the formula shown here to think about that energy as being directly proportional to the frequency of the light. Okay, so a high frequency light shown here oscillates more frequently, and a low frequency light has a longer wavelength, meaning the distance between the trough and the trough is longer. Okay, so we have a less frequent oscillation. We're familiar with the electromagnetic spectra, which places light of all different wavelengths along a spectrum. Okay, visible light is kind of right here in the center. And then at a slightly longer wavelength, we have infrared light. Okay, you may also recall from your general chemistry the formula that the speed of light is equal to the frequency times the wavelength. Okay, and from this correlation, we know that V equals C over lambda. Okay, again showing this relationship that the frequency and the wavelength are inversely proportional. High frequency correlates to short wavelength. If we place that into our original formula, E equals HV, we can think of this as E equals H times C, the speed of light, over lambda. And we see that energy is inversely proportional to wavelength. The longer the wavelength, the lower the energy of the light. So that's our crash course refresher in the correlation between light and energy. Okay. We're not going to focus so much on those mathematical equations. Instead, what we're going to focus on is the fact that organic molecules have the potential to absorb light of the infrared wavelength. Okay. Absorb infrared or IR light. So you might ask why this is. It turns out that the individual bonds within our molecules have the potential to behave like springs. Okay. For instance, I've shown actually an inorganic molecule, HCl, for its simplicity. And I have a small hydrogen attached to a larger chlorine. The bond between them is not necessarily static. The atoms have the potential to vibrate via stretching. And you can imagine that just as if you had a bounce ball on one end and a tennis ball on the other, because of the uneven distribution in weight, that vibration has a characteristic energy. Okay. Turns out that energy perfectly matches the energies of light that we find along the infrared region of the spectra. Okay. So if we irradiate an organic molecule with light, it will absorb very specific wavelengths of that light depending on what bonds the molecule has and how they're vibrating or stretching. Okay, so bonds are able to bend and stretch, and the energy of the IR light matches these movements. The stretching motion that we discussed is shown on the left, and a bending is shown on the right. For the purpose of this course, you don't really need to be so worried about distinguishing when we see absorption, whether it's a stretch or a bend, but more so on how to look at the absorption observed for an organic molecule and correlate it to the functional groups we've come familiar with. So coming back to the idea that the bonds can act as a spring, let's use, for instance, our CO pi bond, which we find in, say, ketones. Okay. What we know is that this bond has a heavier oxygen atom and a slightly lighter carbon atom. Okay. And that this bond can undergo the stretching motion shown in the picture above. Okay. If we were to take a sample of a molecule containing a ketone, such as this shown here, and we were to irradiate the sample with infrared light, we will observe an absorption of the light at the particular frequency around 1700. That is where we see the absorption of light in order to stretch the CO bond. Okay, so let's take a look at what an actual spectrum will look like and how we observe this absorption. So when we look at a IR spectrum, we typically have a percent transmittance on the y-axis, okay? And up at the top is basically 100%. What this means is that IR light is irradiated through my sample, and at a wavelength where I register about 100%, it means that the light simply passed through the spectrum without absorption. Okay, so this top line really means no significant absorption. Okay. Along the x-axis, in wave numbers, we report the frequency corresponding to the different wavelengths of infrared light. Okay, so this is the frequency that we're looking at that point. So the instrument is able to scan the entire infrared region. So it will irradiate your sample with each individual wavelength of light within the IR region. And you will be looking for at each particular wavelength, do I see high transmittance, or do I see what I see here where the transmittance drops well below 50%, indicating absorption of light. Okay. How you're going to read your IR spectrum typically is you're going to pretty much ignore the region between about 500 and 1500. Okay. This is called the fingerprint region. Every molecule that we're concerned with is going to give us signals in there, often many signals. Because of that, it's very difficult to distinguish anything about the molecules from that region. We call it the fingerprint region because it is unique to particular molecules. It's just far too complex for us to dig into. So this is complicated. Don't go digging around in here, okay? You can almost ignore it, okay? Especially at this level of a course, okay? Above 1500, we start to see absorptions that really strongly correlate to particular functional groups. Thus, those signals can tell us a lot about the molecules we're interested in. So for instance, when we have the carbonyl, okay, the CO pi bond, like we discussed for the ketone on the previous slide, we tend to see absorption for that CO bond stretch somewhere between about 1620 and 1750 on our spectrum. So when I'm looking at an IR, I can say, oh, I thought I had an aldehyde or ketone, and now I see this absorption. That confirms for me the presence of that functional group, okay? Other notable absorptions that we're really concerned with in the IR, most organic molecules that we care about have CH bonds, okay? So the CH bond bending and stretching tends to be observed between 28 and 3100. So you are typically going to see signals in that region, okay? The other really diagnostic signals that we're going to be looking for are in this region of about 32 to 3400, okay? That's where we tend to see the stretching of OH bonds and NH bonds, okay? And those become very important signals because a presence of a large signal there will usually help you to confirm alcohols, amines, and carboxylic acids. Okay. Another quick note about the region around 3000. When you have sp3 CHs, they tend to come just to the right or below 3000. And when you have sp2 CHs, they tend to come right around 3000 and to the left of that line. So as you get into finer unknown identifications and you're trying to really match molecules, this can tell you something about whether you're expecting sp3 carbons versus sp2 carbons to be present. Okay, so within the appendix of the lab manual, there's a nice table that's really, really thorough. And again, it walks you through some of the signals you would expect to see for absorption when you have particular aspects present in your molecule. So again, here's your CH bonds. They tend to show stretching between 28 and 3000. I'm not going to go through all of them. I'm going to highlight a few. Again, the really important ones for us, when we see signals between 3100 and 3500, it's typically characteristic of our hydrogen bonding functional groups. So if we're in that region of the IR between 3500 and 3000, when I have an alcohol or a phenol present, it's often true that I will see a smooth, broad peak around 32 to 3300. Okay. There can be a little bit of variation within these numbers. This is usually a prominent absorption signal. Okay. For aldehydes and ketones, as we saw in the previous slide, between about 1620 and 1750, I should also see a prominent clean absorption signal. And these typically will even be down towards like 20 or 30% transmittance. These are very strong absorptions in the IR spectrum. Okay. When you go towards carboxylic acids and amines, you have hydrogen bonding hydrogens in your molecule again. The spectrum starts to look a little different than it does for an ordinary alcohol. So when I have a carboxylic acid in my IR spectrum, in that region around 3200, instead of seeing the nice smooth peak that we saw for the alcohol, it's very common to see the peak be what someone I taught with once called a monster peak. It tends to become less smooth and a lot wider and almost more poorly defined, okay? Wider and messier. Okay. That can be a really telltale signature of a carboxylic acid. This tends to arise from the fact that carboxylic acids themselves have the potential for intramolecular hydrogen bonding, and so they give a different signal in that region. When you get to the amines, when you have what we call a primary amine, a nitrogen that's bound to carbon, but then itself contains two hydrogen, what you tend to notice is that you see an individual signal for each hydrogen. Okay? When you only have one hydrogen, you tend to see one signal. And those tend to come between 32 and 3,500, and they tend to be smoother, like the alcohol signals. Okay? So this messy signal is really a telltale of a carboxylic acid. We're going to do some practice problems in lab. I've uploaded them into the resource folder in case you want to take a look at them in advance, where you will match up the different functional groups to their IR spectrum by looking for these key diagnostic peaks, and you'll use the shape of the peak as one of the identifying characteristics. Okay. Last thing I want to point out in the carboxylic acid region is functional groups can be complex. So the carboxylic acid not only has an OH, but it also has a component within the functional group that has a CO bond, that CO pi bond. We still see the absorption for the CO pi bond in that 1650 to 1750 region, as we did for aldehydes and ketones. So when you see this type of messy peak combined with the 16 to 1700 strong absorption signal for a CO pi bond, when you see both of those present, it's most likely to be that your molecule does in fact contain a carboxylic acid. So we'll see a lot of those in lab this week. And then here are some other odds and ends. The nitro group and the nitrile we tend to work with a little bit less frequently, but you can see that nitriles give a very unique absorption in a region that not much else that we're interested in does. And then nitro groups, you'll also see unique absorption bands lower in the spectrum, kind of more between 15 and 1600 for those NO bonds. You don't need to have these memorized at this point. You can use this chart in lab this week as we work through the practice problems. Okay, so after your solubility test and your IR, you should have a pretty good idea of where your molecule falls on the list of possibilities. So if you think back to the chart we saw in module 1, we have, say, the aldehydes, and we have a long list of molecules. We have our ketones, and we have a list of possibilities. Our carboxylic acids, and a list of possibilities, etc. Okay? So what we'll have from your solubility test and your IR is a pretty good idea of which section of the possibilities you should be concerned with. Let's say that I'm pretty sure I had a carboxylic acid. I saw base solubility in my solubility test. I saw the monster peak and the CO pi bond in my IR data. Now the question becomes, well, if there are 10 possibilities listed under carboxylic acids, how do I know which one is my unknown? Okay. This is where we're going to delve a little more into the specifics of the structure. And the next piece of data we're going to look at is known as a carbon-13 spectrum. Okay. For those of you who continue on to Chem 212, you're going to see a lot of these type of data. Okay. This is known as an NMR, nuclear magnetic resonance. And I'm not going to go through all of the theory of this technique, but what I will tell you is it places the organic molecule in a large magnetic field. Okay. And within this field, odd number nuclei, such as C13, can be analyzed, okay? So we see a signal for every unique type of carbon that's present in our molecule. And here in Chem 211, the most important thing we're going to get out of carbon-13 data is that we're going to count up the number of signals we observe. And based on the number of signals, we will know the number of unique types of carbon within our structure. Okay. This is what an NMR spectrometer looks like. We have one up behind our teaching lab, and I can show you this week if you're interested in seeing it in its real space. These are really powerful instruments. They give us a lot of data, and they're incredibly useful to us. Okay, so let's come back to this idea about thinking of the unique number of carbons that a molecule has. We tend to define a carbon by who its neighbors are. What is it attached to? And how does it differ from the other carbons around it when we look at that? So let's carry out a carbon analysis on this molecule here, phenol. Okay. If I start at the top of my line structure where I've placed the red dot, I have a carbon. And if I play this game, who are my neighbors? I would say, well, this carbon shares a bond to the carbon on the right and the carbon on the left, and it is directly bound to the alcohol portion of the phenol. I'm going to call that carbon number 1. Okay. If I then walk myself down a little further, in blue, I have the carbon next door. So this carbon is bound to carbon number 1, and it's bound to another carbon that is 2 away from number 1. Well, when I go to the other side of the molecule, I find the same relationship. I have a carbon that's bound to carbon number 1, bound to a hydrogen atom, bound to another carbon. You know about resonance now because you've become masters of resonance in class. So you know that I could draw this molecule by pushing the pi bonds around. And so this really, when I consider both resonance structures, it really helps me to see that the 2 carbons with the blue dot are in fact identical to each other. We'll call them both number 2. Okay. In orange, I have these 2 carbons that are now further away from number 1, and we'll call those carbon number 3. And in the hard to see lime green, I'm going to label this as carbon number 4. This is directly opposite, and it's the farthest away from carbon number 1, which is attached to the alcohol. So even though this molecule has 6 carbons, okay, the molecule contains 6 carbons, we say that it has 4 unique carbons, okay, meaning 4 distinct chemical neighborhoods that I can define from one another. So when I look at a carbon spectra from the NMR, I would expect to see 4 signals, okay? So let me show you what these carbon spectrum tend to look like, okay? Like our IR spectrum, they actually have an axis of frequency, okay, that runs along the x-axis. There really is no y-axis measurement in a C13 spectrum, okay? You may see the peaks have differing heights, but at this point, those are not going to bear much meaning to us, okay? So really all we are looking for is how many signals do I see within my spectrum? That's the first question we want to ask. So for instance, in the phenol we looked at, we'd expect 4 of these unique lines. For the molecule cyclohexane, again, It contains 6 carbons, but every carbon is the same. It is a CH2 connected to another CH2 on the left and another CH2 on the right. So we expect to see for this molecule one individual signal. Okay. So again, especially here in Chem 211, the most important thing we're going to look for is how many unique types of carbon. So how many signals do I have in my spectrum? You can dig a little bit further into your C13 spectrum, and you could look at where specifically on this x-axis your signal falls. Okay, so let me erase my drawings here. For instance, let's take the molecule ethanol. I have a carbon shown in red here. That's a CH3 group. And I have the carbon shown in blue that's directly attached to the alcohol functional group. So when we look at ethanol, you should not be surprised to find 2 unique signals in your C13 spectrum. And again, just like in the one above, the signals are always very fine lines that go vertically up and down. Okay. Here, however, you'll notice that there is one signal kind of between 10 and 20, and another signal much closer to 60. Okay. So the final thing we want you to understand about C13 NMR at this point in time is that the neighborhood where your signal is found, okay, we call this a chemical shift. Okay, so the number on the x-axis is dictated by what the carbon is bound to. Okay, so it reflects what that carbon atom is attached to. So for instance, when I'm bound to carbon and hydrogens and I'm an sp3 carbon, I tend to show up in this 0 to 20 sort of region. When I start to get placed next to interesting functional groups like an amine or an oxygen, I tend to live in this region here. So this is my CO or CN bonds, and actually the CN bonds you could even see closer to 40. Okay, so we're not going to dig too much into the chemical shift, but we do want you to be aware that it can help tell the story of your molecule. Okay, so we call this localization on the x-axis an effect of shielding and de-shielding. Basically what it means is if you're in an electron-rich environment, which we consider to be a lot of CH bonds, where electrons are being shared very evenly, we call this upfield, so it's perfectly opposite of what you would expect. The lower number is called upfield. Okay, this is an electron-rich environment. As you move down on your C13 axis, which goes all the way to 220, we call this sort of an electron more poor environment, and we call this downfield. Okay. And we tend to see that we move more downfield as we attach carbon to other electronegative atoms, such as oxygen and nitrogen. Okay, so the CO pi bonds tend to come in this region between 160 and 210. Okay, and this can be very helpful if you thought you had a carboxylic acid or a ketone, and when you get your C13 spectrum, you can look for a signal in this region, and it can help tell you something about whether or not you have that there. Okay. So again, to sort of recap, in a very vague and quick sense, when we have CHs like in propane and butane, we tend to see the carbons here in this 0 to 25 region. As we bind to more electronegative atoms, we tend to see our signals show up more in the 60 region or the 40 to 50 region for a carbon-nitrogen bond. And above 100, this is when we tend to see pi bonds. So first, again, we see our carbon-carbon pi bonds. And in this very downfield region of the spectrum, we see our CO pi bonds. Okay, so this can help us really start to have a nice picture of what our molecule is comprised of. So let's take what we've learned about C13 and see if you could consider the molecules shown on the right. Okay. First thing you want to ask yourself is how many unique carbons does this have? Again, we're just looking for types of carbon. If we follow the same analysis that we did earlier, we have the carbon directly attached to the nitrogen, and we can call both of those 1. Then we have the carbon that is part of this 3-membered ring, also attached to a nitrogen. We can call that 2. And then we have a scenario that we've kind of seen before, where these remaining 2 carbons are both attached to carbon 2, both attached to 2 hydrogens. And so they are chemically the same. We call them 3, okay? So the first thing we know is that we should be looking for how many signals in our C13 spectrum. 3, okay? 3 signals. So when I look at choices A, B, and C, which one can we rule out immediately? If we look closely at B, we have too many signals. Okay, so B cannot be the correct choice for our molecule. Hopefully then, you've narrowed down your choices to A and C. Okay, and at this point you might say, well, okay, the numbers are the same. I can come to this idea about the x-axis representing the chemical neighborhood my carbon lives in. So when I look at carbons 1 and 2, they're both bound to a nitrogen atom. Carbon 3 is a carbon that's only bound to other carbons and hydrogens. Okay, all of the carbons in this molecule are sp3. And so if we take a look back at the previous slides, we would most likely choose C to be the correct spectrum for this molecule, where maybe carbons 1 and 2, which are carbon nitrogen bound, would be in this more downfield region where we see carbons bound to a more electronegative atom. And carbon number 3 here would then be up here closer to 0 because it's really not bound to anything all that interesting. So if you can analyze in this way, you know what you need to know about C13. So if I come back to my hypothetical situation where I think I have a carboxylic acid, I'll obtain my C13 spectrum in lab, and I will say, okay, my carboxylic acid has 4 unique carbons. At that point, I can search for the structures of all of the molecules in the carboxylic acid list and count their number of unique carbons. And I could put a big red line through anything that does not contain that same unique number of types of carbon. And you'll see that your list is really going to start to shrink.